Hello, this is Night Sky Jeff. This is a video about geometry and about the sizes of shadows cast by objects. I'm going to be demonstrating and deriving two, or actually three formulas. They will be the length of an umbra cast by an object, and then deriving the width of that umbra at a given distance from the object, or determining how far into the umbra you are based on the width. So that'll be three different formulas. So I have a diagram here in GeoGebra, which I'd like to go over with you. You have two circles, one centered at A, the other centered at D. We have a tangent line to both of them through B and C, extending to point E. And we have a line between the centers of these two circles from A through D, also meeting at point E. This represents half of the umbral cone created by object D when the sphere or the circle A shines on it. So for example, this is the sun, this is a planet, and this is how far the umbra of that planet extends into space. F is some point along that umbra, and G is a point on the outside of the umbra. F to G is half the width of the umbra at this distance. And you'll notice that this line is perpendicular to the center. It's not perpendicular to the edge. That's how I'm basing the width of the umbra. So I'd like to point out to you, we have some triangles here. We have triangle ABE with a right angle at B. We also have a triangle AHD with a right angle at H. And this triangle is constructed by taking the radius of the smaller circle, which is DC, and subtracting it from the radius of the larger circle, AB. So AB minus DC gives us AH, so that is how we construct this triangle. We have a third triangle, DCE, right angle at C. Now, if you know enough about geometry, you know that these three triangles, ABE, AHD, and DCE, these three triangles are all similar. And how can we know that? We can use angle-angle similarity. We know that the interior angles of a triangle add up to 180. So if you have two triangles and both of them share two angles, then you know that they share the third angle. So for example, if you have a triangle with angles 20 and 30 and another triangle with angles 20 and 30, you know that the third angle of both of those triangles is 130 degrees because 20 plus 30 plus 130 equals 180. So how do we know that ABE is similar to AHD? Well, we know that they're similar because they both have a 90-degree angle, one at H and one at B, and they both share the angle at A. BAE is the same angle as HAD. That means, by angle-angle similarity, that the angle at D is equal to the angle at E. So AHD and ABE are similar triangles. Now, how do we know that they are also similar to the triangle DCE? Well, the triangle ABE shares the angle E with the triangle DCE, and they both have a 90-degree angle at C and at B. That means that angle CDE is equal to angle BAE. So this small triangle is similar to the larger triangle, and this small triangle is similar to the larger triangle. Because one is similar to the other and the second is similar to the third, that means all three triangles are similar. That's great. So what does this gain us? Well, we know that the ratio of, for example, the base to the length is equal to the ratio of this base to this length. And I'm using the radius as the base. It might make more sense to you if I said the base times the altitude. The ratio of the base over the altitude is equal to the ratio of this base over this altitude. So if we want to determine the distance from D to E, we will take the following steps. We are given the distance AD between the two circles, or between the two spheres. And we're given their radii, so we know this length and we know this length. What we don't know is length DE. But because we have similar triangles, we know that the proportion of AH to HD, we know the proportion of AH to AD is equal to the proportion of DC over DE. So let's write that out. We know that AH over HD is equal to DC over DE. Now, what are these values? AH is equal to the larger radius minus the smaller radius. So I'm going to say big R minus little r. That is divided by, I wrote HD here again. I meant AD. Yes. AD is the distance between the two. And we're going to use lowercase d to represent that. That is equal to DC, and DC is simply the smaller radius, over this unknown length, DE, which we're going to call U for the umbral length. We can cross multiply, and we get U times the difference of the radii equals the smaller radius times the distance between the two bodies. And we divide both sides by the difference of the radii, and we get U equals D times R over small r over big R minus little r. So that is the formula you can use to determine the length of an umbra if you know the radius of the light source, the radius of the object, and the distance between their centers. And again, this is assuming ideal spherical bodies. And we can use that assumption with things like the sun and the earth and the moon. So for example, if I wanted to determine the length of the umbra of the earth, given a value of 93 million miles between the two, that would be U equals 93 million. Multiplying that by the radius of the Earth, which we'll say is 3,959 miles, and the difference of the larger radius, which is the sun's, which is 432,000 minus 3,959. And if we plug that into a calculator real quick, excuse my arm, 93 million times 3,959 over 432,000 minus 3,959, we get a value of approximately 860,167.6 miles. So that's how far the Earth's umbra extends into space if the Earth is 93 million miles away from the Sun. Now, we could calculate the min and the max if we take aphelion and perihelion. So let me get those numbers for you. Aphelion and perihelion for the Earth. For the Earth, we'll use 91,402,640. So I'm going to plug that value back in to the equation. Okay, so that's perihelion. So UP is 845,393.4 miles. And the umbra at aphelion value, we're going to use 94,509,460. And that gives us a value of 874,128.8 miles. So it should be clear to you that the closer an object is to the light source, the shorter its umbra will be. And the further away an object is from the light source, the longer the umbra will be. All right, so we have derived the formula for the length of an umbra. The next thing for us to do is to look at point F and determine the length FG, which is going to tell us the width of the umbra at a particular distance F from the center of the body. Now, to do this, we're going to use similar triangles again, but now we need to pay attention to a fourth triangle that we have here. We have the triangle FG, or triangle GFE. The right angle here is at F. So once again, we're going to show that we have two similar triangles using angle-angle similarity. We have the right triangle DCE and the right triangle GFE. So they're both right triangles, which means both of them have a 90-degree angle. And they both share an angle at E. Angle DEC is equal to angle FEG. So we know that we have two similar triangles. So once again, we can use the ratio of side lengths to determine the side that we want. Now, the side that we want in this smaller triangle is, we're going to call it the base of the triangle here. It's FG. Now, this side is proportional to this side here. However, this length is not the hypotenuse. This length is the altitude of the triangle. So we can't use the distance DE, which we determined before. We can't use it directly. We have to do something to it because we need to know this length, CE. So first we're going to get the length of CE with the Pythagorean theorem. We know that the length DC squared plus the length CE squared is equal to the hypotenuse DE squared. So if we move things over, we know that CE squared is equal to the difference between DE squared and DC squared. So what are these lengths? DE is U. We derived U moments ago. DC is simply the radius. And we're going to call This distance, we can call it E for edge. Actually, no, E is a loaded letter. Let's call it G for edge. So G squared is equal to U squared minus R squared. We take the square root of both sides and we get G is equal to the square root of U squared minus R squared. So now we have a way to express this distance CE. So we have DC, CE. We know that point F is a given distance away from the center of the circle. We're going to call that distance V. So we know that FE, the length FE is equal to the length of DE minus the length of DF. So we're going to call, because we need to know FE. So DE is simply U again, and DF, I think I said we're calling that V. This is the distance from the center of the body casting the shadow. And that's where F is. F is a distance of V away from here. And we're going to call FE. We can just call that Z. We don't really care. So if we're given V, then we have all we need. We have an expression for FE, which is U minus V. We're trying to solve FG. We have an expression for DC, and we have an expression for CE. So let's write our ratio. The ratio is DC over CE is equal to FG over FE. We're going to call FG W for the width, or it's really the half width. We're going to multiply by 2 at the end. So let's do our substitutions. We know that DC is R, and we have CE is G, so we call that, or we say that's the square root of U squared minus R squared. FG is the value we're trying to find. We're calling that W for the width, or the half width. And FE is U minus V. So again, we're going to cross multiply. R times U minus V equals W times the square root of U squared minus R squared. And then we can just divide both sides by the square root to isolate W. And we get W is equal to R times U minus V over the square root of U squared minus R squared. And if we want the full width, we just multiply both sides by 2. So we get 2W is equal to 2R times U minus V over the square root of U squared minus R squared. So let's plug some values into this. Let's say we want to know how big the width of the umbra of the Earth is at a distance of 238,900 miles, assuming that the Earth is 93 million miles from the Sun. So we're going to go back to our value for U, which was 860,167.6 miles. Our V is 238,900 miles. We know R is 3,959 miles. So that's R, U, and V. So those are all the values we need to plug into this equation. So let me do that right now in my calculator. All right, so we have 2 times 3959 times 860,167.6 minus 238,900 divided by the square root of 860,167.6 squared minus 3,959 squared. All of that together gives us, again, we're doing 2W. The full width is 5,718.9 miles. So again, this is using, assuming that the Earth is 93 million miles from the Sun, and we're looking at a point 238,900 miles from the center of the Earth. So there you go. There are, and I said I would give you 3 equations. We can isolate V. If you know the width of the umbra, and you want to know how far from the body you are, we can just isolate V. So let's do that. Let's isolate V. We're going to take this same equation. We can cancel out the 2. Actually, let's start right here again. We're going to divide both sides by R. So we get U minus V equals W over R multiplied by the square root of U squared minus R squared. And then we're going to move the U over, and we get negative V equals W over R times the square root of U squared minus R squared minus U. And then we're going to take the negative of both sides, and that gives us V, where the distance you are from the body, is U minus W over R times the square root of U squared minus R squared. I think that is correct. Yeah, that looks right. Yeah, okay. So this is your distance from the body casting the umbra, and this is the width of the umbra if you know how far from the body casting it you are. So yeah, that's geometry. I didn't have to use any trigonometry, although I could have derived the first this first equation. I could have derived this using trigonometry, and I'll do that for you right now. Why not? The trigonometric trick here, we're only barely going to use trigonometry for it. But it's basically realizing that point E is the point such that the angular size of circle D is equal to the angular size of circle A. So the angular size that we're going to use here is the sine. So we're going to call this angle in here alpha, or no, we're going to call it theta. We only have one angle. So we know that sine of theta is equal to the opposite over the hypotenuse. So that's going to be dc over dE. We also know that the sine of theta is equal to AB over AE. So let's do some substitutions here. We know that DC is little r. DE is the distance that we are looking for. We're going to call that D. And we know this is equal to AB is the large radius, R. No, excuse me. This is not D. We're calling this U, the length of the umbra. The distance A to E is AD plus DE. We know that AD is the distance between the two circles or spheres. And we know that the distance DE is U. So we don't even need to calculate the sign. Theta disappears, and again, we cross multiply, and we get R times D plus U is equal to U times big R. So let's see, we're trying to solve for U, so we need to do some expansion here. We have RD plus RU, little RU equals big RU. We're going to move the RU, we're going to move the U terms to one side, and we get RD equals big RU minus little RU. And we can factor out the U. We get big R minus little r. And then that, if we divide both sides by this, we get R times D divided by big R minus little r is equal to U. And you will notice that these two equations are identical, which is a good thing. That's, if you're going to derive an equation and if you're going to derive a formula in two different ways, you want to hope that those two expressions are the same. D times R divided by the difference between the ratios. All right, so this was a different sort of video than I usually do. This is pure mathematics, pure geometry here. But this is, it has practical applications in astronomy. We can use it for determining the size of the eclipse shadow on the Earth during a total solar eclipse. We can use it for determining the size of the Earth's umbra during a lunar eclipse. So there you go. I hope this was interesting. I hope you could follow along what I was doing. This isn't incredibly difficult math. Unfortunately, Kyle Adams is not capable of understanding this. I've tried to explain it to him a number of times, but he can't seem to get it. I'll do another video with these formulas again, basically to show how both he and Potter's Clay are completely mistaken about their thoughts, about their claims about lunar eclipses debunking the globe. If you don't care about any of that, just watch this video. If you do care about the stupidity of flat Earth, I have plenty of other videos about that on my channel. Thank you for watching. If you've made it this far, congratulations. I hope you like this setup. I don't have a digital stylus and pad like that, but I do have an apparatus. You can see it here in front of me. This is for quick scanning in of books and papers and whatnot. And I thought I would use it like this, sort of as an overhead projector kind of thing. I hope to make use of this in similar ways in the future. Again, thank you for watching. I'm Night Sky Jeff, and remember, keep looking up.